Ready? Well, hello, everyone. We are here in the CMS control room. So my name is Lael. I'm a PhD student with the University of Wisconsin-Madison. About 6 months ago, I made the journey from Wisconsin to France to work on my thesis research here at CERN, and I've really loved it so far. Before then, I grew up in Northern Illinois, where I actually found my passion for physics in high school, thanks to some really wonderful teachers. They encouraged me, inspired me. Hopefully today this visit will inspire you. And yeah, looking forward to sharing the experiment with you all.
And I'm Sonia. Very glad to meet you virtually today. I've been a PhD long time ago. But however, I'm come from Italy, from Rome, and okay, there is already a common thing between myself and my colleague, because we are passionate about physics, and this is also my passion that brought me here at CERN. I was lucky to come here to enjoy the physics here and also to continue to be here. I'm currently I don't work directly in CMS, but I've been attached for a long time to another experiment that is called AMS. Maybe as you are from Fermilab, NASA is involved in this experiment. Maybe you know is installed on the International Space Station, but we have the control room here at CERN. And so I think that I can give an objective view this detector, because if I'm here, it's because I like it. It's not just because I work here. It's easy for me, just change a letter from AMS, you go to CMS. And today I will be your guide, underground guide. So I will bring you with me and I will show you why maybe, I don't know, but maybe it's even better to have a virtual visit instead of being here in person. For sure, you will see something that if you would have been in person here, you would have not allowed to see. Okay, that's it.
Right? Okay. So I think then want to also know, just throughout this entire virtual visit, we really encourage you to ask any questions. And we have this Q&A feature, so we try to go through those as we explore CMS together.
If you don't mind, Lael, I will start to prepare myself. So I have to wear the helmet. I already have my shoes. I will prepare, and I will meet you all virtually again with the connection in a few minutes. Bye.
Looking forward to it. Good. So as Sonia gets ready to explore CMS, I can go through and start to give some introductory information about the detector, about the LHC. So to start off with, what we can see here is an overground view of the Large Hadron Collider from above. So right now, we're located in the small village of Cessy, France, where that CMS letter is located. So this is nestled right between the French Jura Mountains to the northwest and the Alps to the southeast. I gotta say, growing up in Illinois, where it's mostly flat cornfields, it was certainly a very pleasant shock to come here and see a mountain for the first time. Pretty amazing, pretty amazing. Even more amazing is what's 100 meters below ground here, which is the CMS experiment. So the CMS experiment is one of four massive particle detectors located along the path of the Large Hadron Collider. And there we have protons traveling close to the speed of light around this 27-kilometer ring. And they come together at these 4 points, they collide. And through that, we sort of understand the nature at the smallest scales ever observed. And CMS is like our high-speed camera that we use to actually gain the information that comes from these proton-proton collisions. And that's in the form of these particle tracks and the energy deposits. What we see on the top right here is our experiment, CMS, and that's 1.4. We have Atlas up in the top left, which is the other sort of general purpose detector. And then Alice is another one which specializes in not the collision of protons, more heavy ions like lead and oxygen. And then to the right is LHCb, which sort of in the name specializes in the study of bee quirks and bee physics. And in the center is the wonderful Large Hadron Collider, which makes it all possible. So again, going back to this slide, DHC is the final ring and actually a full accelerator complex. So this complex itself is a really true museum of science, and it's the home to many important discoveries in the history of particle physics. So it all starts, we have these bunches of protons that fill the Large Hadron Collider. So in total, about 2,800 bunches, each containing about 100 billion protons going around the Large Hadron Collider, super high energy. And when they finally come to a point where they collide, such as in CMS, we have a center mass energy of 13.6 tera electron volts, which is an absolutely huge amount of energy to store in the space of a proton. And with such a large amount of energy available, you can create all sorts of fundamental particles, such as top quarks, Z bosons, Higgs bosons, and perhaps even some fundamental particles that have not yet been discovered, such as dark matter, which is really what we're all hoping for. So it's really great. Good. So I think maybe we see, okay. So I suppose as we continue to wait for Sonia to recreate the experiment, I'm curious if, you know, the acronym of CMS, what it actually stands for. It's all a bit, for an embarrassingly long amount of time, I didn't actually quite know what CMS stood for, but it is Compact Muon Solenoid. And where does that acronym come from? Well, I'll give some hopefully fun facts about CMS. So the whole experiment, the whole detector itself, weighs about 14,000 tons. So pretty heavy. Can't really just pick it up. And dimension-wise, it's about 15 meters high and 21 meters long. So you might say it doesn't sound very compact. It's the size of a whole building, basically, as we pull it up here. Yep. But it's compact in the sense that that is a ton of detector material to fit in that amount of space. It's very compact. Okay. Looks like Sonia's ready to go, so I'll continue on that.
Yes, Lael. Okay, you read my mind. Okay, yes, I'm just ready to enter let's say the experimental zone in on surface. I have the door, the entry door here. Now this access that usually asks for 3 level of checks will ask only 2, but then we have to pass the 3rd also underground. So you will see how we have to do. Now, which are the checks that I have to pass? One is to enter the door. So to open the door, I need to use my personal dosimeter. This one. That is personal. So the system recognizes me. And then, okay, when I enter, I have to step. There is a zone that I would say there is a sort of scale, which, so the system is able to recognize that I'm a person, because this is a door for people, not for material. So, of course, there is a certain range of weight. I enter, but I cannot introduce any material. And so the other check that I have to pass inside is that the system is checking if I have backpack or my helmet is on my head and not in my hand. And so there are infrared beams that are checking that I don't have anything. Okay. Yeah. Yes, and that here we have then there is Noemi with me. But Noemi, she will find a way to let pass also the camera that we have with us. And then there is another system that now I won't use that is the iris check here, the biometrical check, to read my iris and to be again personally recognized. Okay, if you have watched the movie Angel and Demons, maybe you know that, okay, there is something about this, yeah? But there is science fiction. Here is real science, because I tell you that there should be blood inside the eyes, otherwise it doesn't work. But however, I won't use this, so I enter, I try, let's see if I can succeed. The door, they open, I will comment, I step in. And then usually, okay, you see, I just go out. Usually I should stop and do my iris check, but now it's not asked because, okay, we are in a period of shutdown, special period of shutdown. And so they have disabled this function only for this door. Now Noemi, she's also passing. And we go on. We enter in a zone. I would like to show you because if you will have the chance, or maybe you had already the chance to come here to visit this site. We would have brought you exactly here where we have this box, and here we can provide visitors nice orange helmets, unless you are VIP, and so you get blue helmets. Normal visitors also only orange helmets. Here we have other doors, entry doors, again for people, as you see, other two, but it works exactly as the one that I have used. And how you let enter when you come here, because of course your iris are not in the database of CERN, so you cannot enter through the green doors, but we can use the material doors. So we always have, at least myself, I apologize with my visitors, saying that they cannot have to treat them as my material, personal material. And there are two doors. Basically what we do, we open the two doors at the same time. We let the people entering, but let's say for the material, the policy is a little bit different because you open the first door on the other side, you leave the material in the middle, you badge, you enter through as person through the green doors, and then you recover your material on this side. In front of this blue door, there is the elevator, and you see the elevator here is just coming up. Okay, we have 3 levels. I will show you as we are inside, but however, you can see 0 is the surface, -1 is about -80 meters underground, -2 is about -90, and -3 is about -100. We will do our tour between, okay, we will go in many levels, but let's say, I guess that the first level for us will be the -2. Now we enter the elevator here, and okay, here are the buttons. I push the -2. I know that I could lose the connection, so I leave the floor to Lael, and we stick to the display here to show you how deep we go. See you in a few minutes.
Thanks, Sonia. Guys, we'll keep going up here in the control room as they make their exciting way down to the CMS experiment. I remember when I first went that elevator, I think it was definitely the longest elevator ride in my life, but also the most exciting. I'm usually an elevator, it's like, whatever, but wow, going down there, CMS, it was pretty special. It was amazing. And left on a bit of a suspenseful note on the CMS acronym. I'm sure you're all just really dying to know what it is if you don't know already. So what does the M stand for? Let's think about it. My favorite particle, the muon. So we got compact muon, and why is that? Because the CMS experiment was built to detect muons with a very high precision to do that really well. As muon particles came from the proton collisions, be able to measure those very, very good. Finally, the last letter is solenoid. So in the center of CMS, there is the most powerful solenoid magnet ever built in history of the world. 3.8 Tesla field, and we'll get to see maybe some of the effects in the cavern. It's like Sonia's made her way down, so let's go back to her.
Yes, Lael. It took a while because there was also other people inside the elevator, so we had to wait them also to leave the elevator. However, I'm here. Okay, now the elevator is in the other floor below this one. You see almost minus 100 meters, 97. But here we are at minus 87.9. And this.
Oh, looks like we had a slight disconnection with Sonia. Hopefully they'll be back soon. Yeah, I'm sure it should be okay. Okay. I guess in the meantime,
I
got Phil. Oh,
sorry. Yeah. Okay. Yeah. Sorry, because sometimes I lose the connection. Can I continue?
Yep.
Okay, so I was saying that this room is very important for the safety, because here the system is overpressurized exactly as the elevator. What does it mean? That air is pumped outside. So in case here we experience an evacuation alarm because I don't know, there is fire, smoke, or gas leakage, nothing can enter here because everything is pushed out. The stairs, we have, of course, the stairs, they are not protected in this sense. So we have always to stick here to bring the visitors here. And if the elevator usually is guaranteed that it works, we go up. Otherwise, we can wait here. We have all the systems, as you see here. We can also just pull this, lift up this the telephone. We are connected directly with a fireman who asks us what is going on. Then we are followed by all the webcams from the control room where Lael is. And so this is, let's say, stick in mind that this is important place. Now, what I do, I go in the real experimental zone. This is a fire door, very heavy. Now I have to be careful because here people is working. Yes, people is working. So you will really experience not the beautiful place, but a working place, what we are doing. So a lot of mess if you want, but we will go there. But maybe you can see there is a person, maybe you can, I don't know if it's possible to distinguish, there are, I don't know, there is a corridor, is a connection, maybe I can show you when I'm inside the experimental cavern, but there is a connection between the two caverns that we have here. Now I'm in what is called, I guess that usually there is a map that is on the screen. I'm in the what is called the service cavern. There are two parallel caverns. If you look at my hands, they are in that way. I'm in this one, and is long and very long, and is also not so large. And here is the service cavern. Here you put everything you need for your detector. Okay, so electronics, tanks, everything. And then on the other side, here you have another cavern that is shorter and larger, and is where the detector is. And there are different connections between the two caverns. So one is exactly here. Usually it's closed when we have the data taking, but now of course it's open because they are working. Now I proceed here. You see many people all around, and now we enter the counting room. The counting room is the one of the rooms where you can find the electronics. There is this room with electronics. There is another one on the top floor here, exactly in this position. And there is another big one on the other side, opposite from the location I am, that say it's more or less the sum of these two. And then, of course, we have other electronic surface and attached to the detector. Lael, if you want to say something, now I see I came here. Yes, exactly. I'm a little bit sad because when I came here the last time, we had still collisions. So here was connected and working. Now everything is dismantled, everything is detached. There is no noise, anything. But however, okay, it's always nice to go through and to see standard cables, optical fibers, and you know, in normal, if you would have been here, is not allowed to come through these corridors, okay? So visitors cannot enter. So it's, in any case, it's special. Even if you, okay, no visitors are allowed now to come here, but even if you would have been, you cannot come in the corridors. I just checking because there are barriers. Maybe we go back in the same way. Yes, because when there are barriers, we have to respect. This is oops. Yes, in fact, this is the safety rules. Yeah. Okay. Let's see some other. Yes, still something here. Yes, okay, do not touch. This is still connected. Did I remove also the, no, okay, we can talk about this. You see these orange bands. These are a special, let's say, signals, if you want, that we use to recognize if there is a power cut. There is some electronics that is not switched off. And these orange bands are exactly saying that even if there is a power cut, the things are working inside. So we have not to touch unless you switch off with the special buttons that are exactly inside here. So I will show you the general button that stops everything, but not these orange, okay, cables. Let's pay attention. Okay. Yes. And you see, we could push this button. We stop everything, but the electronics that they have these signals with the orange bands. Now here there is my preferred cabling. Yes, cabling wall. I don't know if we can. No, we cannot. Okay, so you have to believe me. Please believe me. Yeah, because no, because this is the Mona Lisa of cabling. Yes. Okay. Yes. Okay. Now close your. Yeah, I cannot show you. I cannot touch. Safety. Okay, is protected. There is a reason. I don't know the reason, but okay, I believe my colleagues. However, all the wall is red, and there are. I don't know how many cables, but what is really amazing is the regularity of these cables. What I mean, they are connected in a special shape. Each cable has a special length because it should be not too tight and not too loose. Each cable has a label. So frankly, it takes, I would say, I did cabling with the optical fibers. These are standard cables, but I can say that, okay, you could spend easily half a day just to cable, to do the cabling of half of this one column of this wall. And it could seem to be boring. It's not, because frankly, there is a lot of preparation before. You have to think how you have to connect, and then you have to do the job. You have to become, is a sort of Zen exercise, I would say, to become, not to be disturbed. And when at the end of the day, you switch the button on and everything works, you say, okay, I did my job today. It's really, really amazing, this wall. And this is why I call it the Mona Lisa of the cabling. Just to tell you, it's related, and maybe Lael, then he will talk about this, is related to the to one of the sub-detectors of the CMS, that is the one in the edge, is the muon chambers. So it's giving the power to the muon chamber. Now we proceed. This is another corridor that connects to the two caverns, okay? And we have another door. This door, this works properly. Is it correct, Noemi? Yes. So here, yes. So here I have to do also.
So it looks like the connection got a little spotty again. I suppose as we wait for that one to come back up, I think we take this opportunity to ask if you all have any questions, really just anything on your minds, or maybe something you're really excited to see as you get to see CMS.
How many miles of cable is there?
Oh,
Kilometers.
well, I think so. There's 120 million channels in the
Exactly.
experiment.
telling this is a little bit hard. Telling that what would happen if you would put together a single core cable with a multi-core and how long it would be. I think what we could say that it would go around the equator, that's for sure.
Oh yeah.
But obviously, this is just a number.
Yeah. So I guess in conclusion, quite a lot. I think Sonia is back.
Sonia is back.
Yes, I'm waiting. Yeah.
Okay, we lost her again.
I guess this is definitely a pretty
comes and goes.
Yeah, pretty spotty part of the cavern, but that's very good question. Anything else?
Doesn't like that we are doing this, so we have this beep beep beep.
Oh, yeah.
You may, yeah. Okay, we go and we go to the cavern. You see? Can you hear us?
Yeah. Yep.
Yeah. Okay. Yes. So we are almost inside the cavern. As you see, there is the corridor. Now, this is, if you want, in such a way, the equivalent of the other corridor that we have seen, but I'm one level higher, okay? Because the corridor I was showing before is in the level below, and we will go just now in the level. Now, I open the door, again, very heavy door, and I enter the cavern, and I show you the baby. Yes. Still a bit closed, not.
I've gotten cut off again here. Let's see.
Just add you on the spotlight.
Oh yeah.
To allow her.
Very good.
Yep.
But you got to see. I guess I don't know if you can still see this.
Yes, but we can. Now we have people here working. Maybe okay, we can already show people in. Then we will be there. This is the basement, the -100, and here we have one part of the detector that is still closed. Now, if you can see, the detector is going from this part. We will go down on this side, and here. Let's see if I can do with in this place. Yes, exactly. Okay. Maybe you can see, if you pay attention, the beam pipe that is just entering the detector here.
We can show it from the top.
Yes. Then we go on the top there. Yes, okay, sorry, I'm trying to do. We go on this balcony and we will show from the top the beam pipe. But however, okay, this means that the LHC is this one. Now, this is not a let's say scientifically correct, but I think that we can use also daily life comparison to give an idea of what we have. Now, just imagine an horizontal kebab and the stick in the middle of the kebab. So the LHC is the stick and the meat is the meat of the kebab is the experiment. Yes, okay, we have to do in that way. Sorry, because we are just doing. No, I mean we go in this way. Yes, okay. So I walk close by the detector, and if you see, there are these structures, these green structures. Now you see there is one is here and finished there. You see, so I don't know, I would say 2 meters, more or less, 2.5 meters. You see, from here to here. And then I have another one from here to here. Now, these are slices. So the detector is a huge, yes, these are, the detector was built as a huge Lego that was assembled here in the cavern. This is because the total assembly of the detector was done totally on surface. But there was no chance, and there are no cranes that can bring down a detector of the weight of 14,000 tons below in one shot. So each slice was lowered one by one, and the detector was rebuilt. So you could imagine the detector was on the top, the first slice was lowered down and pushed back toward the wall, and then the second one again, and the detector was rebuilt. And these are the slices that you see. I hope that, okay, if we can continue. These are objects that we will meet times to times along our path. These are geodetic instrumentations to check, you see, the geodesic points. And these are to measure that if there are movements of the cavern, okay? Because what is really important is that the cavern must be stable. The detector, in order to guarantee the precision and that all the parts of the inner part of the detector are not moving, because otherwise our measurements are not precise, we need to check that this cavern is stable, doesn't move, okay, cannot shake. The other cavern, the service cavern, can shake, but not this one. Now I continue. The detector is ended. We have, okay, the path is more or less between 21 and 24 meters, so a building of 7 or 8 floors. It depends what we count together. And here you see that we still have this orange structure that is really closed, is a shielding. On the other side, you will see the same. Maybe I can do with my hands. So imagine that you have the beam pipe coming towards you. So this object is closing the beam pipe. On the other side is opened as a butterfly. Okay, you will see on the other side, as we go on the top of the balcony, you will see that this object is open. And this is to shield the forward part of the detector where we can get a lot of radiation when there are collisions. We go down. We go up. Okay, so we go up first. Now, consider that the diameter of the detector is 15 meters, which means a building of 5 floors. So I'm just doing some gym and reaching, we are still on the top. I would say we are at the 4th floor. I continue. I go back again beside the detector. Again, you see other electronics, but this electronics is inside the cavern, which means also should be suitable for a high radiation background. And then we go on the top to the 5th floor. I continue to, I like a lot to be here. I always enjoy, and I tell you, now I will ride the detector. Where I can go, okay, you see here, now Noemi, she's showing you that we are really on the top, 5th floor, you see? And now, okay, where we go? Here on the other side.
Whatever. Yeah, thanks.
Here, okay, yes. So look what I'm doing. I'm here, and now I jump on the top of the detector. This you cannot do. This is only for the virtual visits. I go here, and then there are, you see, stairs. Where I can go? There, here, yeah. Okay. Follow me. And I'm almost at the top of the detector. Okay.
Okay, Noemi,
I'm
Sonia, please look out the crane.
Yes. Oh, but not so tall. However, yes, I see. In case we will need. However, you see, we are on the top of the detector. We are riding the detector. I was joking with Lael before. I was saying is, as you know, this famous scene you see in the movie Titanic, you know, when they are on the top of the boat, not sinking, of course. Yes. Now, okay, there are many interesting things to see apart the electronics. The first thing that is really amazing, then I will show you also from another position, is the shaft. You see the shaft here. This one is from where they lowered these slices I was talking about before. The diameter is, I would say, exactly apart 10 centimeters left and 10 centimeters on the right, the diameter of the detector. So you could imagine that these slices, each of them between, depending on which slice it was, let's say between 1,000 and 2,000 tons, was lowered here very carefully, taking sometimes 8 hours or 12 hours, avoiding, of course, to start an oscillation as a pendulum. Otherwise, you destroy everything. And okay, you know, if you have only 10 centimeters on the left, 10 centimeters on the right, you would like to be very careful. And so this job was done when they lowered the detector. And then there is another interesting thing that we can see here are these red stuff that you see on the walls. This is the last hope, I would say. What I mean now, of course, we have many safety systems that are working in case there is a fire, there is an issue, in particular fire. So each part of the electronics has its own. But of course, it could happen if you are unlucky that you cannot switch off the fire locally. So consider the last choice that you have to yes, kill the fire for the detector. So from here you have foam coming out and is completely covering the detector. Or maybe, I don't know, just to remain to the food comparison, imagine a huge Swiss roll covered by cream, okay? Because you cover completely the detector. Now, it could, if you think about, it seems to be nice. It's really catastrophic because this foam has a powder inside, so that enters everywhere. And so at this point, your detector becomes something for a museum. You cannot use it anymore. You cannot clean it. So let's say that we know that the system is continuously checked. We know that it works. It was, the simulation was done before the detector was here. And is the famous foam party that was called. But then, okay, we cross fingers that we have not to use it because otherwise we don't know exactly what happens of the detector. But they are here. You see, there are many of this stuff all around to kill the fire. Yes, okay, maybe you can see the gap in between. Now, Noemi, she's showing, you see, so the dark part that you see is the gap between each slice. We have two, we call them as slice, we call wheels also. And we are on the top of one, and we have the next one in front of us. And the dark part that you see is the distance in between the two wheels. I will show you also coming down now, the space left on the side, that is the space between the wall and the detector, the famous, let's say, 10 centimeters I was talking about, because here is exactly this one. Look. Okay, you can see here. I can put my hand, you see? This is my hand. I don't have a huge hand, okay? It's a normal hand, let's say. Okay, this is the space left This is the wall of the shaft, and this is the edge of the wheel, the slice of the detector, okay? And this is what was left on both sides, left and right, when we were lowering the detector. Noemi, she's also, yes, Noemi, she's showing, I don't know if you can see again, what is in between the two wheels. Of course, there is connection. Everything is connected, but I should say that sometimes, now they are doing mechanical works, but it happens that these wheels, these slices, they can be opened as an accordion, you know? And you open where you need. Of course, you detach things and then you have to close back in a precise way for the next measurements. We have some parts, you see, some mechanical things, and now we go on the balcony to show you the beam pipe. I wait for Noemi going down. So we go down from the 5th floor, and now we go more or less to the 4. Just here. Is another view of the detector. Now I show you where we were before. Before, when we entered the cavern, we were where you see the two people there. Okay, the balcony. And this is the only place where the visitors, they can go. They stop there. They stop there. They cannot do the tour I'm doing. Now, okay, the beam pipe here, we cannot have, okay, maybe here. I don't know, maybe here. Yes, I guess that here we can see. If you remember, I was trying to show you this part before, okay? So you still see some structures, but maybe here, I don't know if you can distinguish, there is yes, is a sort the color is as copper, let's say, but okay, there are some tape. Yeah, is a tape that is a Kapton tape for protection. Okay, yes, okay, yes, okay. And this is the beam pipe, so the stick of the kebab I was talking. Now, of course, when you enter the experiment, you have one beam pipe because you want a collision. So you have one beam coming from this side, the other beam coming from the opposite side, and they cross in the center of the detector. But as they go out, then they, with the help of magnets, they split again on two beam pipes, okay? Because in general, LHC has two parallel beam pipes. And only when you access the detector, you go in one beam pipe. Yes, okay. Maybe we can give another nice picture view, another view of the shaft. Yeah. We don't need for the shaft is enough big. We don't need the zoom. And you see also the ventilation. Consider that now you see that there is light, is bright because it's open. Usually it's closed on the top of the shaft. It's totally closed because you could imagine if there is activity, we are protecting on the zone. So, and there is a mobile floor. Can we go to the assembly hall or not? Yeah. Okay. Okay. Okay, so we have to go down now. If we have time, otherwise I tell you here, so it's not okay. In any case, we cannot walk on the floor, but however, there is a movable floor that is closing completely the top of the shaft. And now it's open. Yes. Okay. Yes, we go very fast to the minus 100. So the -3 level. Enjoy the view from the camera. Noemi, she's showing how we go down. And Yes, so we have some barriers, but maybe we can profit to show you another interesting things that is here. I think that here is enough clear, and then we go closer. Are these orange structures that you see there? Yes, here. And then you have also others there, but there are also others that you cannot see here inside. Now, if you look carefully, you have this structure. Then we go closer. There are also some tubes here. And these objects are very useful to move, to slide the wheels up and down, okay? I will show you how we do. We go down. Can we go? I guess yes. We are, okay. I show you this structure. Now you see, consider I'm 1.60 m. Don't ask me in feet, okay, please. Don't ask me to convert, but you see the detector, okay? So this is what I would call one of the feet of the detector. I was telling you this is the pad, and here you have these tubes. Now, I told you that each wheel, each slice can be opened in that way. So you need to move back and forward the slice, and these you do through these pads. How do? You put some grease below, so this helps, and also you pump compressed air from these tubes inside, and basically what you do not lift, but let's say you make it a little bit lighter, and then what you do, you have cables. Yes, okay, we cannot see here. I will show you, however, I can mimic a little bit. We have some cables that are attached here, and they pull the slice. Is a sort of horizontal crane that is pulling, so you could imagine is a little bit lighter, and there is the grease. Let's go on the other side, and we will show you these small cranes. Here, you see? Now, we don't have the cables here, but however, yes, this is the machine. There are big cables, 6 big cables, and you can pull. Now, what is important is also to understand that when you close.
So the connection might be just a slight bit off here at this point.
Yeah, exactly. Probably the reception is not good enough.
Yeah.
So if you could move out, if you hear me, could you please move out from that place for a better reception?
Oh, there we go.
Yeah.
We're back.
Can you have us now?
Yep.
Now
Do you
it's
have us?
much better.
Okay.
Yeah.
Thank you.
Yes. Okay. Sorry. We go in that way. We go in that way. Okay. We can just show the cables, just to show how big they are. Look at my hand. But are similar, no? Yeah. Are similar, no? Yeah. Okay, you see, this is one cable. I don't want to touch too much because they are greasy. Yeah. And now, okay, I want to play with my clips. If I have can you hear me better?
Yes, absolutely.
Yep.
Yeah, okay, so we are now on the opposite side, but I have again one. I told you there are many of these feet. Yes. So, okay, let's, but I have my proper one. Let's see what happens. I have my personal, okay, of course. You know equations, you know magnetic fields, you know how things they are going, but why we cannot enjoy just to experience physics as a 5-year-old child? Okay, let's see.
So I
You
think,
see, this is a residual magnetic field. And now we'll try to do a little bit better with other stuff. Okay, yes. Let's see if I can do. Okay. Let's
Sonia,
see in that.
I think,
Yeah.
while you are doing this very nice game, I would recommend for asking for questions as well. I would keep you
Yeah.
on. So
Yeah, they can ask. Yes, okay. I enjoy myself. I lose myself now doing this.
exactly.
You see?
This is
Look,
the point where we
this is
usually
new.
lose the guides.
Look, this is new because now you see it's not just oscillation. I can also do, you see, the spinning. Look, the spinning.
Cool.
You see?
Cool.
Yeah. You see? Okay.
Okay. So in the
I love
meantime,
this moment.
I would ask for questions, and
Yeah.
please continue this in the meantime.
Yes, I continue. Yeah, of course. You cannot stop me. You cannot stop me. Look. Okay, I can collect them. Let's see
I
what
put you
happens
back
in
on the
that
full
way.
screen.
Yeah. Yeah. This is the residual magnetic field, because this is the magnet is off. Let's see if I can use my friend here. I have two friends here. I have now. You see, we have this nice duck, which is provided by a clip. And usually, I tell you, when the magnet is on here, if we keep the duck, I don't know if Noemi can show my hand. If we keep the duck in that way, in this position, I do here because I don't want really it's flying, but the duck goes up alone, just flies, okay? Of course, now it's not possible because the magnetic field is not enough. So the only thing that I can offer is the butt duck that I have. And let's try here. Yes, okay, it works. The butt duck. Okay, I told you now I'm 5 years old. I know. Look, you can enjoy, and this is how universal is physics and science in general. But I think if I think that
Sonia,
you
I
think the
you
same,
won.
yeah. Yeah, you see the bad duck? Yes, okay. I have the normal duck and the bad duck. Okay, yes. I don't know. I don't know what happens. No, this is not enough.
No, this is too
Yeah.
But you can hang the normal. Yeah, exactly.
Yes,
That's
I can do both.
abnormal.
Yes, okay. Yes, okay. Yeah, AB normal as Frankenstein Jr. AB normal. You know, I was just thinking about this. Okay, this is nice. And but you see, okay, this is the way we capture, for example, students. Most of them, if we talk about equations, they start to get bored. But if you show this, you can capture them really. Okay, and you see, this is now, yeah. It's a kind of magic. Now we go to music from movies. We go to music now. It's a kind of magic. And in fact, okay, maybe what I can say is that at CMS, when in the control room where Lael is, and maybe Zoltan, he knows, or Noemi, they know who put the music, because when there is the data taking, sometimes it happens something in the program. I don't know, there is a detection or somebody is stopping the data taking.
These are the DAQ guys, and they play Queen music indeed.
Yes, exactly.
We are the champions means that we started the DAQ.
Wow.
Yeah, and when you stop the run, you say don't stop me now, and it's a kind of magic. I would guess there should be something interesting. Yeah. So exactly. You see, so yes, exactly. I totally approve because I'm a fan of Queen too. So for me, it was the best choice. Do you know, Zoltan, who did this? Which guy?
I don't know the name, but these are the DAQ guys. They all insist to have this on. But you see, on the other hand, if you are on shift and you listen to the same snippet for several tens of times, maybe 100 times per per shift. Well, this might a little bit make you to rethink of your relation to pain.
Yeah.
Yeah, I don't know. You see what I'm experiencing that now, you see, is very slow, the oscillation. You see?
Yeah. In the
see it?
meantime, I would like to propose go for questions. Sorry
Yes.
for ruining down everything. So
No.
if you have questions in Fermilab, I think the dance floor is yours there. Yeah.
What's the most number of paper clips you've been able to put on there?
Oh,
Sorry. I don't know if the
Most number of?
the most number of paper clips you've been able to chain in the CMS.
Yes.
I think it's
Okay.
order of
Now.
10, but it depends very much on the position where she starts from.
Yeah.
At the edge
Yes.
of this foot, obviously you get a bit higher field than on the top of the foot. The top of the foot is good enough to shut down my Mac. Mac screen, even though this is very appealing for working.
Are you speaking from experience?
Yes, exactly. Yes, exactly. A sad experience. You know that's an obvious place to put down your computer to do something, but that's the point where you can't.
Exactly. Now, however,
you got a good trend there.
You see
Okay,
this?
that's more than 10.
Yeah, and this is let's say, of course, roughly has been calibrated outside the cavern with Noemi. When there was the magnetic field here inside the cavern, where there was the yellow door, the second one that I passed, because there we can still feel the magnetic field, and we tried to see which was the maximum number of clips we could attach outside, and this is the maximum. But I see that corresponds more or less. I don't know, if you want, I can do some experience here for you, just to answer your question. Let's see if I add another clip here, maybe. Okay,
actually,
let me
for
find
those who love the numbers, what we are talking about at that edge is maximum 100 millitesla, maximum at this moment. If we, however, we turn on the magnet at the edge, we can go up to half a Tesla. That's sizable. That will attract not only the paper clips, but rather the standard field indicator that we take in when we can go in when the field is on. That's a M19 spanner.
No.
Strictly that.
It seems is the maximum even here, you see? I cannot attach. Okay, another one. Another one by the dust. Just to remain to the queen. Yeah. And I don't know. Now I have two couples. I don't know if I can succeed. Let's see. And I think I will stop because otherwise. Okay, no.
Oh.
It seems to be too much. Okay.
Okay, so the gravity is a weak force, a very weak one.
Yeah.
Strong enough.
Yeah.
I think this is really showcasing the beauty of CMS. I mean, we have the most powerful solenoid magnet ever made. Niobium titanium probably costs what, like $1 million something.
Yeah,
and we're playing with paper clips.
The board is something like 6 meters. I think it is probably physically the biggest.
Yeah.
I think. Well, I had a discussion with my old professor. I told this is maybe the biggest. He claims it is the biggest. Obviously, concerning the field, there are magnets that are stronger than this one.
Yeah.
But with this board, this is for surely the strongest. When the field is on inside the solenoid, we have 3.8 Tesla, which is comparable to the a mid-size MRI machine field.
Mm-hmm.
Once we had an interesting visit, I guided a group from one of the MRI producers, and I told them that, look, this is capable of doing what you do, but on an elephant. They loved me.
Wow. Wow.
I had a question regarding the CERN updates. We learned yesterday that one of the things that you're going to be doing for that big update, like the current shutdown, is that you're going to be getting higher field magnets. Do you know how strong your new magnets are going to be?
So first of all, we are going to replace the so-called finer focus magnets. Some of them were produced in Fermilab, I think. These are the magnets that
this is on the Large Hadron Collider.
Exactly, the Large Hadron Collider, not about the detectors.
Okay.
These are the magnets that focus down the beam to something like a couple of tens of microns in order to have the luminosity. And actually, this is the reason why we want to replace them with stronger ones. They will get the niobium tritium technology, and the technological limit is somewhere around 15 Tesla. Instead of the more or less than 9 point something that we have currently in the niobium titanium.
I have a question.
Zoltan, can I just say something, just to ask you if I can leave the cavern because I can come up?
Yes, and that soon after we get the
okay.
question.
Okay. So I go and you continue with the questions.
Okay.
Sonia, go ahead.
Yes.
My question is the following. You said that the detector has to be very aligned. That's why you have these indicators on the sides to make sure that everything is aligned. I don't know if there are any earthquakes in the area, but if yes, how does this structure respond to a possible earthquake?
So what happens, I know the statistical answer. We do not expect more than one Richter scale 5 earthquake here in this region per thousands of years. So that means that we are on a very stable, even though we are in front of the Mont Blanc, a tectonically unstable region, this is quite stable. I already, since the LHC is on during the past almost 20 years, we didn't observe a large earthquake here. During the lab era, we had one not too far from here, and the L3, well, not the magnet, the support tube started to move a little bit, but this was not significant either. So the answer is that all our infrastructure is made against the Richter scale 5 in order to preserve the human life. However, what we have to keep in mind that since we are not producing GDP, if anything comes misaligned, then we have time to realign. Mm-hmm. That's a very important thing. GDP is the question, not the Richter scale.
Yeah, Zoltan, if I can just add, is not related to the earthquake, but maybe, okay, it's interesting to say that, however, there is the monitoring that we have about this stuff. For example, because, okay, we are talking about movements as earthquake, but you could imagine also that we have the moon tides. So the earth tides.
Yes.
Yeah.
Also,
and these are also there. Yeah, they are monitored and they are corrected. So the beam that they have to collide, they are corrected. Otherwise, you cannot really smash them.
Exactly, and also the seasonal change of the Lake Geneva that obviously deforms the rocks. And also there is one more thing that usually people don't think of. Don't forget that these are large cavities in a solid material, and they have a buoyancy. Mm. Of course, we do not expect the LHC tunnel to surface during the next 1,000 years or even more, but there is a sizable, measurable buoyancy effect, what the survey follows, because you might imagine that in the CMS cavern, the CMS detector's weight, this 14,000 tons, this balances the buoyancy. So this cavity doesn't move. In contrary, the accelerator tube is not balanced. It surfaces, it goes up. Therefore, it brings up a little bit the beam level that we see in the detector, and its negative effect on the pixel is that part of the pixel gets more irradiated than the other part. Therefore, we always have to be at least in the awareness that this happens. Survey people follow these differences. We have several survey solutions for that, and that is obviously limited, but that is a way to adjust the beam height in the accelerator in order to compensate it.
Yes, and in fact, okay, just to show you, and then I really leave from this place, otherwise I will sleep here this night. We were, if you can see on the top, I entered from Noemi, she's showing you, and we are going towards again the service cavern. The service cavern is also not, let's say, so stable. So only the cavern, the experimental cavern, is monitored as Zoltan was saying. All the rest is briefing, I would say, up and down, and everything is monitored to avoid that the central one that we are where we are now moves for the detection. And this, I told you, okay, this can be done. I call people from LHC wizards for this, because I think they are doing a lot of things. I don't know what my colleagues, they think, but okay. Now, we go out, however. And
okay, I think we can turn back to the questions.
Yes, exactly. Lael, if you want, as I have to go out, if you take the floor and just because I cannot hear very well the questions from here, in case you call me.
Of course. Sounds good. So yeah, I think any other questions or comments or anything like that?
Yeah, so with the CMS shut down right now, as she was giving us the tour, was she getting more, less, or about the same radiation exposure as she'd get at the surface?
It's a good question. In my mind, I don't know the exact numbers. I think there'd be very, very slight residual radiation, but at this point, I think it would be roughly about the same. Yeah. And of course, this is why we're the dosimeters. So periodically you should check that, at least I'd say once a week, the one that they're scanning right now. And that'll tell you very specifically how much radiation you've accumulated on that dosimeter. And that's how we keep track of these sort of things. But CERN is, I know, very, very, focused on safety. So I think they would never let anyone down there, of course, during any sort of level of radiation that would cause damage. So hopefully that answers the question. Zoltan, I don't know if you know the numbers, but
yes, I can show you now. I will go. Okay, unfortunately, I didn't check. I didn't show you the checking of the dosimeter before entering, but I can show you now. Okay, as we go up, there is the machine. I can show is this one. But this is not the only one. This is the personal one. Is a sort of integral. You sum up the dose, and you must make a reading in 1 month. Okay, between 1 month you have to do, otherwise you receive a reminder. And of course you have to avoid to bring these objects on flight. Sometimes, we are used to fly, and there was somebody that was flying to US, I guess Fermilab, and forgot in in your bag this. And when he came back, he was just checking. And the checking, what it happened was that the system realized that there was a lot of radiation. And as the machine is directly connected to the medical center at CERN, they immediately called him, I guess was a guy, to say, okay, to ask what was going on, where he was, because, okay, they thought that there was a problem at CERN. No, it was just, yeah. Here, maybe it's cutting the connection, so I leave you the floor.
Sure.
I think the connection stays, but anyway, I keep
we can
question.
Yeah.
Very good question.
We have maybe time for one more. We're getting a little low on time.
I have a question for my students. Could you tell me the various types of careers and occupations are used to build, create, or operate the facility there?
Oh yeah,
That's a very good question.
Very good
So
question.
normally people think that we need physicists only. This is not true. What we need is everyone who is interested in technology and science. Therefore, not only physicists but engineers included as well.
Yeah.
Every type of engineers. Of course, you can imagine we need IT. We need electronics engineers, but we also need mechanical engineers. Just regard the pictures that we had on the detector. Definitely, this is a not normal engineering task. So all those people welcome who are willing to design something weird like this. But apart from this, if you consider that we have quite a few civil engineering tasks as well, even civil engineers are important for us. So I would say that everyone who wants to work on science and technology should move to CERN, work with us or for us or whatever.
Yeah, I'd say certainly every part of the acronym STEM, you can find plenty of people here at CERN. And you might even say, I mean, it's like a huge company, so with tons of people. So even non-STEM careers, there's plenty of them that you can find at CERN. So hopefully that answers the question. Yeah, so it looks like you're at the dosimeter station.
Yeah, exactly.
Can I show the reading?
Oh yeah.
I
please.
think I'm just going to put you on a full screen.
Yeah. So this is my dosimeter. I put here.
On this dosimeter, we have one ionization chamber. That's what Sonia is reading out now, 0.9 millisievert. When your dosimeter was replaced, Sonia?
What is replaced in March?
In March.
So this is 4 months, more or less.
4 months. We are talking about 1 millisievert. The legal limit per year is 3 millisieverts for everyone, including us, not just the normal population. Out of that, we get minimum 2 from the natural radioactivity. And you might imagine that how small it is for a person who regularly goes underground to the cavern.
Yeah.
Okay, now these data have been transmitted to the medical center, and everything
and to
is
the
fine.
database. Your radiation passport knows about it. That's a European regulation.
We should say that we have to enter, and we need another dosimeter because this is a passive dosimeter. It means that it's not telling you if something is going wrong inside the place. We have the other dosimeter. I don't know if there inside we can show you.
Yeah, you can pick up from here in the control room.
Yeah, I'm coming because I'm close to the control room, and so this dosimeter that I will show you, this is beeping. So in case there is an anomaly, you will be. You see, this is the dosimeter. Okay. You see?
So these are the so-called active dosimeters. We assign them not only to person, but also the work package the person is working on, so that we can get a much more granular view about the radiation doses the workers get. And as Sonia told, and due to the active dosimeter type of this can annoy you if you would get accidentally more than the limits. I never heard it in alarm, by the way.
Can I say something very quickly? Yeah, it happened to me not in this site. I was guiding in the antimatter factory, and it happened to me that I had a group of engineers, and at a certain point, this dosimeter gives you a beep times 2 times just to say I'm alive, I'm working. So in case there is a problem, I will tell you. But they didn't know. So they start to be scared because they heard beep. I had to explain them that, okay, this was a regular beeping just to say, okay, it's active and ready to detect any anomaly. Yes, can be annoying. Zoltan is perfectly
Yes,
right. It can be
definitely.
annoying.
Yes, definitely. This is one point that I never make a joke of,
Mhm.
even though I
Yeah.
like to make jokes. I might scare people, and I do not want. That's so good that we are in our community together with you guys, that we all know about the radiation. For normal, ordinary mortals, we obviously we would not go into such a detail. We do not want to scare people. Without reason. Yeah. Next question.
I think we have to wrap it up. We thank you for being available for so many questions, though.
Yes, thank you.
Thank you.
Thank you.
As you see, I'm alive.
Back.
All right.
Hope it was a very good visit. Hope inspiring, educational, all that, and hopefully take it back, inspire all the students. I think it's really great. So thank you all.
Thank you very much.
Yes, thank you also from my side. And okay, very interesting questions. Those I could pick through the connection. And I hope to meet you in person. I was just saying that already happened in the past edition, that some of you were participating to the program that we have here at CERN. So maybe we'll meet in person, but you will never have the chance to see what you're seeing today.
Exactly.
Sonia.
We will all hope so.
Thank you.
And thank you as always for being so open to share what you do and educate the public. It's fantastic.
Okay, thank you.
Thank you so much.
Thank you.
Have a nice day.
Bye.
Ciao, ciao. See you soon.